Welcome back, everyone. We are going to continue where we left off with 4.3. I have not started grading the test yet, but I'm gonna try to knock them all out tomorrow. Cause I don't have anything until Friday night lab tomorrow night. Uh. It takes you would be surprised how long it takes to grade a second test. It's an adventure. We were working on 4.3, I'll call this 4.3B. We were graphing rational functions. And I'm not gonna rewrite the list. But this is the list we made. When we were talking about what steps to take. We're gonna just do some more problems. You have it in your notes from last time. Let's take a look at, let's graph. F of x equals x squared plus 3 over x. So, step one, find the domain. It looks like the only violation to the domain we have is. X cannot equal 0 from the denominator. So we're gonna have we're good everywhere else. This means x cannot equal 0 means no y-intercept. Right? Can we have an x-intercept? That's step 2, find the intercepts. Can we have an x-intercept? If we have an x-intercept. It's where the function equals 0. So x squared plus 3 over x equals 0. I'm not even worried about the bottom. It's really where the top equals 0. And if you look at it, we have two positive numbers. There's no way that adds to 0. But if you tried to solve it, you get x squared equals -3. And if you take the square root of that, you get plus or minus I root 3. Get some complex numbers. So no x-intercept either. That's fun. Okay, now we want to look for asymptotes. It looks like we have a vertical asymptote. When x equals 0, because that's where the denominator equals 0. And if we look at our notes for horizontal. Our numerator is 1 greater than the bottom, which is what this one says. So we're gonna have an oblique or a slant asymptote. I'm gonna go over both ways to do it, because one way is easier, but it only works in a specific one. The easiest way to do this one is. To break this up into x squared over x plus 3 over x. So I get x plus 3 over x. Or x plus 3x to the -1. The point is, these horizontal or vertical asymptotes. Vertical, horizontal or oblique asymptotes happen as the limit as x goes to infinity. Excuse me. The limit as x goes to 0 or infinity of x plus 3 over x. That goes to 0. So it's going to infinity along x, and we knew that. Cause the numerator is bigger, but. This tells us what the graph looks like. Graph looks like y equals x for large values of x. For example, if x equals 1000, y equals 1000 plus 3 over 1000. What is that, 1000.003? It looks like y equals x at that point. So we're in oblique asymptote, we also call those slant asymptotes. Because that's what's gonna happen. So let's sketch what we've got so far. We don't have any intercepts, but we do have x equals 0, or the y-axis is an asymptote. I'm trying to put that in right next to it. And then y equals x, which is the perfect diagonal. This is my oblique asymptote. Okay, so now we wanna find, we're looking at finding critical points. Regions of increase or decrease in concavity. So I have f of x equals that. I think it's gonna be easier to do the derivative if I start with it in this form. Rather than doing the big one. F prime of x will be 1 minus 3x to the negative 2. Or 1 minus 3 over x squared. And I think finding the stuff we want to look for is easier if I get a common denominator here of x squared, put it together. That way we can find, when we're doing the critical points, we gotta set this equal to 0, and this is easier if it's one big fraction. So f prime of x equals 0. It's when the numerator equals 0. And we're gonna get x equals plus or minus the square root of 3. So let's take a look on the number line, what's going on with that. We've got negative square root of 3, positive square root of 3. This is about 1.7-ish. So we'll do some test points real quick. 0, negative 10, and 10. The bottom's always positive, so the bottom's irrelevant here. That makes sense? So if the bottom is squared, so it's always positive, so it's not gonna affect the signs. We're just doing a sign chart right now. So I'm only gonna look at the top. Negative 10 squared is 100, minus 3 is 97. That makes this region positive. While I can't technically stick in 0 for the denominator, it will show me what's going on at the top. Well, let's not do 0, I don't wanna do 0, let's do 1. Let's do 1. The bottom's still positive, 1 is between those two values. 1 squared minus 3 is negative 2, that makes this a negative region. And if we stick in 10, we're back to positive. And this is the first derivative is giving us slope. So up until square root of 3 is positive. And then we've got it going downward from there. We've got some stuff like that going on. It looks like negative root 3 will be a local max. And positive root 3 will be a local min. Does that make sense? Does it ring a bell? I know it's been a while, like about a week since we looked at this. With the group tests and stuff, so. Got questions, say so. Okay, so second derivative. I will again do off that one. The one in the easiest form is off of 1 minus 3x to the negative 2. This becomes 6x to the negative 3. Which shows this is 6 over x cubed. And it looks like 0 might be breaking things up. So this is in the bottom. It does make a false, like a somewhat of a critical point. Things can change signs there. I should have done 0 here. I can't just ignore it. And do -1 and +1. The same would have happened, we still would have had negatives. But the bottom does create, or like, things to look at. If we go to the left of it, and -1 makes this -6. And we go +1, this makes this +6. So it's gonna be concave down to the left. And concave up to the right. This is like -√3 and +√3. One other thing I'm gonna do that I think will help us, it's not necessary, I'll show you the argument why in a second. But let's do a sign chart for just f of x. When x is negative. This is a negative thing. And when x is positive. This is a positive thing. Which means it's gonna be above the y-axis on the right. And below the y-axis, or not y-axis, x-axis. And below the x-axis on the left. Does that make sense? F of x is our y values. And if they're all negative to the left of 0, we're in the negative region. So we're gonna combine this all together. We know it's concave up on the right. And it's increasing. Like from there, and it's coming down. From 0 to square root of 3, it's doing some shit like that. And then following the asymptote, I got a little too close to that. That's not, I didn't wanna get that close, but oh well. And then it's gonna do some shit like this on the other side where it's negative, concave down. Okay, so without doing that sign chart. We could have still deduced that. The asymptotes tell us what the guiding behavior is, and on the right side. I can either be doing something like that, or I could do something like this. Maybe I'll do that in pencil. It's either. From the concave up, it's doing that, or it's doing that. Just by guiding the asymptotes, the concave up one says choose that one. On the left, it could be doing something like this with the asymptotes, or something like we had with the asymptotes. And the concave down is saying do this one. So the sign chart wasn't absolutely necessary, but it does help. Doing this sign chart does confirm that we're above the y-axis to the right, below the y-axis. Fuck, I keep saying y-axis. Below the x-axis and above the x-axis. If it makes you feel better, 4.4 that we're doing today is gonna be so much easier. It's a fucking cakewalk next to this. All right, you guys ready for some more? Got another quality example for you. But before we, something else I wanted to show or state. We had f of x equals x squared plus 3 over x. This was the last problem. And we did this by breaking it up like this over this. That is not the only way to break this to get the x plus 3 over x. The other way of doing this is you divide the bottom into the top. Doing long division. This gives me an x, multiply, I get x squared, I subtract, I got 0. I got 0 here, so 0 there, and x doesn't go into this, so this is my remainder. And so what's on top is like that, and the remainder goes over the old denominator. The reason why I pointed out is because we can do this works here. But not here. You see, does that make sense? It's not as helpful. Here, we actually have to do the long division to find out what it is. Now, it should still give us an x. But in more complicated things, it may give us something that isn't as obvious. So long division sometimes is the only way. When you're graphing these, you do have something else that it can pop up. If f of x is continuous at x naught. But f prime of x is not. Like f prime of x is dne. Like there's no derivative there. That's what I wanted to say, but f prime of x is dne, it does not exist, there's no derivative of x naught. Then f has a vertical tangent line at x naught. Not an asymptote, a tangent line. So this is usually like. Some examples, we could have something where the function is doing this. And at x naught. It needs to come in and be a little bit more like that. But x naught right there is giving us a tangent line. Same thing if the graph is going upward.
Yeah, by tangent line, you mean where the change happens in direction, right?
It's where the slope,
Or is it equal to 0?
the slope is not gonna exist. So like this, tangent line is an awkward way of saying it because we're so used to seeing tangent lines touch something but not cross it. But when you have a vertical tangent line, it actually crosses it. So here's my x naught tangent line there, it's going upwards, but also at a cusp. Tangent line to the cusp. Like if we do a sign chart, I'll do a sign chart below it. This is negative right here, but it goes positive here. Starting to go up. Here, the slope is increasing and then it gets to x naught and it starts decreasing. And we can see this is negative and then positive. And this one is positive and then negative. The slope is changing, but it doesn't go through zero to do it. Like on this one, it could be like -10, -5, -1, -0.1, -0.0001. And it doesn't hit zero like every other slope does. Or the derivative goes, it just immediately jumps over to positive, it goes up to positive. And it's because there's a cusp there or a vertical tangent line. An example is probably the easiest way to see what's going on. So let's take, I'll do another page here. F of x equals. X minus 2 to the 2/3. Now. There's no negative exponent here, so there's nothing in the denominator, which means. This has a domain of negative infinity to infinity. We don't have any domain violations. This is also like saying the cube root of x minus 2 squared. That's another way of looking at it. The reason why I say that is. The inside gets squared and becomes positive no matter what x we use. And then taking the cube root of a positive number is always positive. The range is gonna be 0 to infinity. And if I stick in 2, I actually have 0.
Can you repeat what the domain or the domain restrictions would be? It would be.
There's none.
But if we had one, would it just be if it was X? Or is there a?
It's when domain restrictions are when the denominator equals 0. If there is a square root that has a negative on the inside.
Okay.
0 works on the inside, but a square root that has a negative on the inside generates complex numbers. We can't generate and draw that in the real number. Stuff. Those are like your two main things to look for domain restrictions.
Okay.
Now, if we look at the derivative here, though, we've got 2/3 x minus 2 to the negative 1/3 times the derivative of the inside. But that just equals 1. Like the inside is x minus 2, so that's 1. But another way of writing this one is 2/3 times the cube root of x minus 2. And now at x equals 2, f prime of x does not exist.
Again, how would you know that x equals 2 at this point?
Set the denominator equal to 0. If you set the denominator equal to 0, you're looking for. This will find domain violation. Set the bottom. Equal to 0 for. DNE. And solving this, divide by 3, we got cube root of x minus 2 equals 0. We cube both sides. We get x minus 2 equals 0. And then add 2 to both sides, you're gonna get x equals 2. And we look at a sign chart there. 2 is the only spot something changes. It's the only spot where any x is, so it's the only thing to look for. If I stick in like 0. I have the cube root of -2. Cube roots, odd roots, you can have a negative on the inside, just even roots. But the cube root of a negative number, like cube root of -1 is -1. Maybe that's a better one to use, we'll use -1. So this denominator is negative, that makes this whole thing negative. So we've got a slope going downward. To the left. And if we stick in like 10. The denominator is gonna be positive, cube root of 8 is 2. That's positive. So the right side is plus. And this will be up. We're gonna look at concavities, let's take the second derivative. We bring the power down. And lower the power by 1. Shakes it down to -4/3. And you take the derivative of the inside again. But that equals 1 and we get -2/9. And then 1 over the cube root of x minus 2 to the 4th power. Again. And for the same reasons, x doesn't equal 2 in the second derivative. That becomes our. Switch point for concavity. So I'll try -1 again and 10 again. If I stick in -1. This becomes -3, but to the 4th power is positive. In fact, this whole thing is gonna be positive no matter what. Because this is always to the 4th power, it's an even one, it's always positive. But the negative out front is gonna make it concave downward everywhere. Okay, so. We got x equals 2 here. To the left of 2. We have an m is less than 0, the slope is negative. And it's concave down. Slope less than 0 means it can do this. Or it can do this. Both of those have a negative slope. The concave down one is saying this one. To the right of 2. We have m is greater than 0, which means it can do this. Or it can do this. Both of those have a positive slope. Concave down is saying it's doing this. So going into, we know at 2 it equals 0. Because the equation, if I stick in 2 up here, f of 2 equals 0. And if it's doing this to the left, it's coming in like this. And if it's doing this to the right, it's coming out like that.
What about the point where it crosses the y-axis?
We can figure it out by setting the equal to 0, but that wasn't what was really different about this. So we can find the y-intercept. Find what? Find y-intercept, not by setting equal to 0, but letting x equal 0. So f of 0 is -2 to the 2/3, which is 4 to the 1/3, or cube root of 4, whatever the hell that is. One point three, somewhere less than 1.5, I think. Alright, let's do one more. Everyone ready? Are we all excited? It's a Thursday, your week's almost over. You don't have to see my bright and shining face unless you come on Saturday. That should make you sad. Oh, Pat, there's a lot of people online. Alright, so domain, all the exponents are positive, which means we don't have any issues there. I can stick every number in and I should get a valid thing. I don't have any even roots. This is the same as 4 times the cube root of x. Minus the cube root of x to the 4th. So I take the cube root of any value, negative or positive. I don't have any domain violations for that. I don't have anything in the denominator. Domain is full number line. Or all reals, as they like to say. If we want to find the zeros, we want to find our x and y intercept. Well, y intercept is easy. Y-intercept, x equals 0. And. I get 4 times 0 minus 0 is 0. So 0, 0 is our y-intercept. It looks like it's one of our x-intercepts now too.
Is that 4 times 0?
Yeah,
Oh, okay.
because if I stick in 0 for x, I have the cube root of 0. Yeah, it kind of looks like 4.0, doesn't it?
Yeah, that is.
And if you want x equals 0, or the x-intercept, we need to set y equals 0. So 4 times x to the 1/3 minus x to the 4/3 equals 0. It might have been a while since you've done this, but when you have fucked up exponents. But there's something there, a variable for all the terms, we can factor out. The lowest exponent. If it's present in all of them. X to the 1/3 is the lowest exponent. If I pull that out, I have 4. Minus. And I'll do this as a sidebar. X to the 4/3 over x to the 1/3. This is 4/3 minus 1/3. Which is 3/3, which is 1. Just x. So I did a little sidebar action here. So this is giving us an x-intercept at 0 from that one. Or 4 minus x equals 0. And this gives us x equals 4 when we're done. So we have another point at 4, 0. And these are our two intercepts. Wait, I wrote that backwards. I'm doing y-intercept there. There we go. Nope. Fuck, I had it right the first time. What? Y equals 0. I'm doing x-intercept. I was doing it correct. Don't you just love when you fucking beat yourself a couple times in a row on some shit you know how to do? Have you ever said your name or heard your name so many times in a row that your name sounds funny? Or said a word like a word repeatedly and all of a sudden you're like, doesn't fucking sound right. A simple word like the. Say the like 100 times in a row and all of a sudden it sounds like you're pronouncing it wrong. That's kind of shit just happened there. Okay, so we've got our domain, we've got our intercepts. We want to look for asymptotes. There is no vertical asymptote here. It doesn't look, because there's no denominator. Someone wave. Wow, hateful. Hateful room, there we go. Thank you. There's no vertical asymptote because there's no denominator. And that kind of makes it so there's no horizontal asymptote. Yeah,
I just noticed, since there's an x to the 4th, wouldn't the x-intercept also include -4? Or would it just be positive?
it's just positive because we factored it out. Now you're fucking with my head. Let's check it real quick. F of -4 is 4 times the cube root of -4. Minus. X to the 4/3 is x times cube root of x. So I have minus and then x is -4. Times the cube root of -4. This gives me a plus and then I have 8 of them. So that's not a 0. Not 0. So you can always plug it in and check. If you're like, this seems wrong, something's off, always plug it in, check. There's a lot of people walking by. Hi, everybody. Someone wave. Great. Alright, now we're looking for critical points where shit's changing. Since we don't have any asymptotes. So we had f of x, I'm gonna rewrite it here because it's easier to see it. While we take the derivative. We bring the power down. 4 times 1/3 is 4/3, and we lower the power by 1. And we bring the power down here, and we lower the power by 1. And we're gonna do the same thing we did last time. I am going to, well, it looks like I can factor out a 4/3. And I can also factor out the lowest exponent, which is -2/3.
That equation is the derivative of the top one, right?
Yes, sir. I can factor out the -2/3. If I pull it out of that one, that just leaves me a 1. On the second one, just like we had here, you're doing 1/3 minus the thing you factored out, minus -2/3, should give us another x. To the first. Yeah, put that in. Alright, so we have a 0, well, we have a critical point here. At x equals 0. And this is gonna be something that. Since it's in the denominator, cause this is. 4/3 cube root of x squared. This one, it's gonna be one of those vertical tangent lines. At x equals 0. And this one just gives us a critical point at x equals 1 when we set it equals 0. Okay, so let's do our number line. 0 and 1. And that might be easier to look with the. Cube root of x squared there times 1 minus x. So if I stick in a negative number. Like -10. We have 4/3 times the cube root of 100. Times 1 minus -10. Which looks positive. Because 1 minus -10, that's 11, cube root of 100, I don't know what it is, but it's positive. We don't have any negative signs there. If I stick in 1/2. That root is always gonna be positive because it's an x squared inside. The only thing that's changing is this, 1 minus 1/2. Is positive. And sticking like 10. Got 1 minus 10 is negative. So this doesn't sound like a cusp, it sounds like the line just keeps increasing. It's got a positive slope the whole way, it just sounds like it's like. Like something like this. At x equals 0. Increasing and increasing. Alright, second derivative. I'm gonna have -8/9 x to the -5/3 minus 4/9 x to the -2/3 if I factor out a -4/9 that's present in both. And I also factor out the lowest exponent, which is the most negative one. This will leave behind a 2 on the first one, because we had -8 when we divided by -4. And this one, we've been off by a single power every time, and that's not changing. It's been. That should be negative though. No, they were both negative here, so that is positive. So again, x equals 0. And here we're gonna have x equals -2. We're looking for concavity now. That is -4/9. Then I got 1 over the cube root of x to the 5th. And then 2 plus x. This thing is gonna have whatever sign we stick in. Raising something to an odd power and then taking the cube root is never gonna change the sign. But we get a negative from this one. And whatever happens here. So if I do like -10. I get a negative from the -4/9. I get a negative from the cube root. And 2 minus 10 is gonna be a negative from that parentheses. This is a negative region. So concave down. I stick in -1. Again, negative. But 2 minus 1 is positive. So that becomes a positive region or concave up. And if I stick in a positive like 1. The -4/9 is always negative. The cube root is always positive. And 2 plus 1 is positive. This is a negative region or concave down. And now we have everything we need to graph. Other than one thing. You're gonna see that as we start graphing it. We had asymptote, or not asymptotes, we had intercepts here and there. We have a critical point at x equals 1, which means. The slope changes, which means we've got a max or a min there. It just might help to plug in f of 1 and find out what we got. So at 1, we have y equals 3. Now, we look at our slope. If it's increasing as it goes up to 0. It's doing this. Which means it's gotta be coming like that. Maybe I should have done that in pencil, because we have some concavity issues there too. At -2. Where's that at? F of -2. Is 4 times -2 to the 1/3. Minus -2 to the 4/3. Now it's back to. Cube root of -2. Cube root of -2. Okay. 4 times answer. This is about -7.5. So it's way down there. I'll just say that's at -7.5. We had concavity between -2 and 0 being positive. So concavity between -2 and 0 is doing some shit like that. That's coming from this. So ignore the red line. The concavity to the left of -2 was downward. And the concavity to the right of 0 was downward as well. We know it's gotta go up to 2. And come down. And do some shit like that. Probably a little more like that. Over here, talking about the shit. And these are called the inflection points from that second derivative. It's not perfect, but it gives us a good idea where everything's at. And let's take a 10-minute break before we start 4.4. I'm actually gonna stop the video and restart it as a separate video since they're